Assalamualaikum warahmatullahi wabarakatuh and good morning to Dr. Hamdan Muhammad Yusuf. We are from Group 12 Air Major. Now we would like to present you the presentation of integrated project entitled Production of Anhydrous ST Acid. This is the list of Group 12 members. My name is Syifaa Amani Binti Abdul and my matrix number is 200772.
My name is Bita Abedi and my metric number is 204364.
And my name is Heng Guan Wei. My metric number is 202453.
Hi, my name is Nursyafiqah Binti Muhammad Isa. My metric number is 202728.
In this presentation, it will be divided into 6 sections. The first section will be the introduction. The second one is process description, and then will be followed by distillation column design, safety analysis, costing, and the last one is conclusion and recommendation. Before we continue our presentation, I would like to express our gratitude to Dr. Hamdan Muhammad Yusuf, to Dr. Muhammad Rezi, and also Professor Dr. Zurina for their guidance and advices in making this project successful. Now I will present you the first section, which is the introduction. The objective of our design project is to produce 99% of purity anhydrous ST acid by having a production capacity of 1 million tons, an input of around 698,000 tons per year of ethylene, the average output of 114,000 kilogram per hour of ST acid is obtained. So the company's aim is to plan the proper selection of routes in order to produce ST acid and design different ways in order to reduce the requirement of energy in order to improve the profitability of our processes. So through calculations and analysis, we found out that the cash flow analysis for 20 years is done to estimate the profit that can be obtained by the production of ST acid for every year. The average revenue is calculated based on the operating costs and sales of ST acid, assuming that the capital cost is neglected. Hence, the average revenue is calculated to achieve 37 billion ringgit, which includes the catalyst and absorbent costs. So, based from the graph, ST acid has a demand of USD 8.92 billion in the year of 2019 and is expected to grow at a compound annual growth rate CAGR of 5.2% from the year of 2020 to 2027. So, what actually is the uses of ST acid? It is used in vinyl acetate, solvent for the production of your terephthalic acid, PTA, acetate anhydride, acetates, and others. So, in our process design plan, there are 16 units of process equipment added not only to produce desired production quality of anhydrous ST acid, but also to comply with the environmental safety. Now I will pass the presentation to Guan Wei.
Okay, now I will talk about the process description. Okay, next. Okay, the first one is the heater. Okay, the purpose of the heater is used to increase the temperature of component before it entering the next unit. It is assumed that there will be no pressure change during the heating process. In addition, a countercurrent shell and tube heat exchanger will be used as our heater instead of using an electric heater. This is because the heat exchanger has lower operating costs but produce the same heating effect as an electric heater. Therefore, it is more preferable. However, if high temperature is required, then an electric heater might be a better choice. Next. Now let's look at the heater one. Heater one, it is used to preheat the raw ethylene from 25 degrees Celsius to 150 degrees Celsius. The heat that is required to be absorbed by cold water is required to it is heat that required to be heat the heat the raw ethylene is 832 kilojoule per second from the hot steam, while the heater 2 used to heat up the air from 25 degrees Celsius to 150 degrees Celsius. The heat that required to be released from the hot steam is 2781.2 kilojoule per second. While heater 3 is used to heat up the mixture of MTBE and acetic acid from 26.87 degrees Celsius to 51 degrees Celsius. The heat that is required to be released from hot steam is 383 kilojoule per second. Okay, next. While the compressor, generally compressors are used to increase the pressure of an incoming stream at the corresponding temperature. In our design, isothermal compression is used. In order to simplify the calculation, we assume all the gaseous components that behave as ideal gas. However, in expert simulation, PSRK method is used and the efficiency selected is 1. The compressor operates isothermally and isentropically since the volume is not constant. Next. The compressor 1 is used to compress the raw ethylene from 1 atm to 5 atm. The compressor power is 1.494 kilowatt, which means that 1.494 kilojoule per second of energy is required to compress the raw ethylene gas from 1 atm to 5 atm. While the compressor 2 is used to compress air from 1 atm to 5 atm as well. The compressor power is 7,354 kilowatt. Okay, next. Now let us look at the first reactor. The reactor 1 is used to yield ethanol from ethylene hydration with the presence of phosphoric acid as catalyst. The unit function at 5 atm and temperature of 150 degrees Celsius. The conversion of ethylene into ethanol is assumed to be 5%, only even with the presence of catalyst. Around 54,000 mole per hour of the raw ethylene is compressed and sent into reactor 1 to be reacted with water to produce ethanol. Okay, next. While reactor 2 the aims of reactor 2 is to conduct the direct oxidation process and oxidation of ethanol into acetic acid. The PD GA 0.005 something is our catalyst that will be used in this reactor. This catalyst has the selectivity of 80.1% to form acetic acid and 15.6% to form carbon dioxide, while 4.1% form acetaldehyde. The reason why part of the ethylene is first converted into ethanol instead of direct oxidation of ethylene is because the conversion from ethanol is as high as it reached 90%. In reactor 2, air is the limiting agent. Reactor 2 operates at 150 degrees Celsius and 5 atm. Okay, next. Now let us look at the vaporizer. The vaporizer is used to boil liquid water into steam. Vaporizer temperature is 150 degrees Celsius at pressure of 1 atm. Around 19,000 mole per hour of water is vaporized before it goes into reactor 1. The vaporizer is similar to heater, however, it has to deal with phase change of a substance. The power of this unit is 2,576 kilowatt. Okay, next. Next, The next column is separator. It accommodates the products from second reactor and separates them at the dew point of the mixture. The equipment is working based on the different volatility of components and their corresponding vapor pressure. The calculation of this unit are done using Antoine equation in order to calculate the dew point. From the calculations, it is found that the working condition of this equipment is at 114.43 degrees Celsius and 5 atm. Water is circulated through a jacket surrounding the separator to absorb the heat release and maintain the temperature of the unit. 6,459.3 kilojoule of heat per second is required to be absorbed in order to cool and condense the hot gas product. Hence, the condensate consists the composition as shown here, which is 0.6649 mole of acetic acid and 0.3327 mole percent of water and 0.002 mole percent of acetaldehyde and 0.0004 mole percent of ethanol. Next. The next one is the cooler. Cooler is used to reduce the temperature of product stream by exchanging heat with the cold water. As heat exchanger type cooler is used in this plant to save the operating costs. Since water is a cheap source of coolant, which has high heat capacity and achieve the same degree of cooling compared to other coolant. Next. Cooler 1 used to cool crude acetic acid from 114.43 degrees Celsius to 25 degrees Celsius at constant pressure. The heat release from the hot crude acetic acid is 32,619.5 kilojoule per second, while cooler 2 is used to cool low purity acetic acid from 87.3 degrees Celsius to 51 degrees Celsius at constant pressure. The heat release is 542.33 kilojoule per second. Next. The next one is the pressure reducing valve. It is a specialized plant being used which control the pressure. And when we calculate the temperature increase after the pressure reducing valve, we assume that it is functioned adiabatically. So that's why the pressure of the stream will increase in temperature. Next. Pressure reducing valve 1 used to reduce the pressure of crude acetic acid from 5 atm to 1 atm. The temperature increased from 25 degrees Celsius to 25.166 degrees Celsius. While the pressure reducing valve 2 used to reduce pressure of low purity acid from 10.42 to 1 atm. Its temperature increased from 51 degrees Celsius to 51.38 degrees Celsius. Next. Now let us look at the right-hand column. The binary mixtures of acetic acid and water with composition of 0.665 mole percent of acetic acid and 0.335 mole percent of water is fed into the right-hand column. It is desired to obtain a bottom product with 0.88 acetic acid and 0.12 water. However, the distillate consists of 0.2 mole percent of acetic acid and 0.8 mole percent of water. In order to achieve this separation, a reflux ratio of 2.67 is used. From McCaptil graphical method, the theoretical trace that determined to be the theoretical trace they are determined to be 10.3 trace plus 1 reboiler. Moreover, the feed will be entered at this column at the 7th tray from top. The condenser operates at 100.2 degrees Celsius which is the dew point of the distillate, and at 1 atm, while the reboiler operates at 114.83 degrees Celsius, which is the boiling point of the bottoms at 1 atm. Okay, next. Now is the extraction column, which is also known as the liquid-liquid extraction column. It's used to separate the compounds based on their relative solubilities. The techniques selectively dissolve one or more compounds into an appropriate solvent. The solution of these dissolved compounds are referred to as extract, while the aqueous phase is referred to as raffinate. The solvent used in this context is MTBE. MTBE has been identified as the best solvent used for extraction of acetic acid from water due to its high selectivity, low density, and low heat of vaporization. The extraction process works at temperature and pressure of 51 degrees Celsius and 1 atm respectively. Next. The aim of this column is to recover the extracting agent, MTBE, and in turn purify the anhydrous acetic acid that has 0.9997% of acetic acid. Next. Now, this one is the splitter. Splitter is an ideal separation device. It splits specified compounds into predefined fractions. In our case, it is used to split portions of recovered MTBE to be recycled back at a recycle ratio of 0.051. This equipment is assumed to operate mechanically, therefore no energy, no work, or heat is required for release. Okay, next. Now I will talk about the recycle stream. Now, why we need to recycle the MTBE? Because according to Sano, MTBE is one of the best solvents that can be used to extract acetic acid. The working principle of liquid-liquid extraction is based on the different solubility of acetic acid in MTBE and water. Thus, this makes the separation process possible. However, the market price of MTBE is expensive. Therefore, the usage of MTBE must be planned well. To cut down the expenses, part of the MTBE must be recovered and be recycled back. Next. You guys may wonder how we select the recycle ratio for our splitter. The effectiveness of the extraction column is highly dependent on the concentration of extract in order to achieve higher order of purification. Hence, the recycle ratio to purge, flow rate, recover MTBE must be controlled to avoid excessive acetic acid being recycled back. Otherwise, this would reduce the separation efficiency in the extraction column. It is assumed that the compositions of acetic acid in the extract must be less than or equals to 0.005 mole fractions of acetic acid to guarantee the performance of extraction column. After doing the mass balance calculation, around 25,000 mole per hour of MTBE will be recycled back. The ratio of recycle is found to be 0.051 millimole. The amount of fresh MTBE required is around 440,000 mole per hour to maintain the input ratio of MTBE to acetic acid at 1.5. That's all from me. Thank you. Now I will pass to Bita, my teammate, to proceed with the next part. Thank you.
Okay, thank you, Guan Wei. I will proceed with the distillation column design. So as you can see, and here is the light end column, which Guan Wei already explained the function. So I will just proceed with the explanation. So it is used to separate a fluid mixture depending on its volatilities. Based from this figure shown, these distillate products are substances that have low boiling point, meanwhile the bottom product are the product that have high boiling point. So the inlet coming into the right hand column is actually the binary mixture of 0.665 mole percent of acetic acid as well as 0.335 mole percent of water at an operating condition of 25 Celsius and 1 atm. So in the design column calculation, we use McCabe-Thiele graphical method. It is used to indicate the number of theoretical trays for us to achieve the desired product. A reflux ratio of 2.67 is used to achieve this separation. This graph gives the value of the theoretical plates, which is 0.33 plus 1 reboiler, and it is determined that the feed enter is actually from tray 7. So here is the mechanical drawing of distillation column tower. So after calculation, we found out the column dimension, which is the area, is found out to be 0.48 meters square, and their height is 20.07 meter, as well as the diameter is 0.78 meter. So based from this first picture, we can see this is the front view. And for the second one is the side view, where we can see the sieve plates are arranged accordingly, and there are 18 trays. So why is 18 trays? As I already mentioned before, that we calculated it to be 10.3 trays. So depending on its depending on its tray efficiency, so we calculated the number of actual trays is to be 18 trays. So that's why I drew the plates to be 18 trays with the height of 20.07 meters. So this drawing is actually drew in millimeters. So for the internal view, we can see there is trays that are placed between arranged considerably, and then for the outer view, you can see that feed is coming into the 7th tray, and we also have reflux liquid reform as well as reboiler return. So the mechanical drawing for the distillation column sieve plates. So here is the drawing where we can found the plate parameters, and the efficiency is 0.5544, and the plate materials is mild steel, and the plate spacing, which is the plate between each other, is 0.6 meter, and their thickness is 5 millimeter. And for the hole, the number of the holes is 1,858 holes. So what do we make to make our design more feasible is it is best for column's height to be less than 53 meters due to its foundation and also wind load considerations. It is also a space should be considered at the bottom and top for the reboiler return and also the vapor release. The next one is the best common tray spacing is between 0.508 to 0.910 meter. Columns with larger number of space than 115 are considered infeasible. In addition, between 1.1 and 1.5 times the minimal reflux ratio is the ideal reflux ratio range. Columns that operate outside this range will cause a dry up of liquid or vapor at a certain number of trays and will affect the separation process. Done with the design of distillation column, I will pass with my next presentation, with my next presenter.
All right, thank you very much, Syifaa. So now I'm going to explain about the safety analysis. All right, so the first point to consider is the health analysis. EHS stands for Environment, Health, and Safety. It's a broad phrase that refers to laws, rules, regulations, professions, programs, and workplace initiatives aimed to protect employees and also for public health and safety, as well as the environment against workplace dangers. So, in conclusion of the MSDS table obtained in our report, shows that most components need to be handled with care as they can cause irritations, dizziness, drowsiness, respiratory tracts, or nausea and vomiting. Next, please. Thank you. So for the safety analysis, we can see that according to the tables obtained, most of the chemicals and components which we are using in our plant are highly flammable, but they are low in toxicity. These components need to be kept away from hot surfaces, sparks, flames, smoke, oxidizing materials, acids, and ignition. A note to be considered is that acetaldehyde and MTB are considered as very toxic chemicals, thus proper precautions need to be taken, such as wearing gloves, masks, and goggles. Furthermore, any processes that takes place in the plant need to be in a fully closed space in order to prevent any gas leakage to the outside environment. Next, please. Thank you. For the environmental analysis, we could say that emissions from the chemicals, they can cause climate change due to the high release of CO2. Emissions can pollute the air or they can also cause smog. Toxic chemicals can cause groundwater pollution. Wastewater needs to be prevented from entering the drains or sewage. It can cause water pollution. Certain chemicals are harmful to aquatic life, so we need to be careful to reduce these emissions as much as possible and not to release our wastes into the environment and also into the water. Thank you. I will now pass it to Syifaa.
Next, we will move to the costing part, which include capital cost, working capital, utilities costing, cash flow analysis, and market analysis. For the first one, which is the capital cost, for the capital cost, it will include the equipment costing, utilities, and fixed operational costs. For this proposed design project, our group has used 16 units, which include 3 heaters, 2 cooler, 2 compressor, 2 reactors, 2 pressure reducer valve, a vaporizer, a line and column, a extraction column, a solvent recovery column, and a separator, also a splitter for a recycle process. Total price for all equipment costing has been shown on the slide. Next, we will move to the utilities costing. For the utilities, it will include the electricity, cooling water, processed water, and fuel. And it is determined to be 1.02 billion Malaysian ringgit. Next, for fixed operational costs, which include labor, plant overhead, and laboratory, all of these will take up to 20% of the total operating costs. Operating costs will be divided into 2, which are total operating costs with and without catalyst. For operating costs with catalyst, cost of catalyst such as palladium and phosphoric acid will be added up. For the total operating costs without catalyst, no cost of catalyst will be added. It is possible because catalyst is a substance that will not be destroyed at the end of the reaction. Hence, it can be used again. Next, we will move to the working capital. For this part, I will explain about the summarize of fixed operational costs, which include mainly labor, plant overhead, and laboratory. It is estimated to be 20% of the total operating costs, which include catalyst. For total fixed operational costs, it is estimated to be 5.7 billion Malaysia ringgit per year of production of acetic acid. Next, which is the utilities costing and sales of acetic acid. For this part, costing for raw materials, absorbent, catalyst, and utilities will be summarized. Basically, cost of raw material, which is ethylene, is estimated to be 1.4 billion Malaysia ringgit. While for the absorbent that will be used in this project, which is MTBE, is approximate to be 326 million Malaysian ringgit. There are two catalysts which is palladium and phosphoric acid, which cost determined to be 26 billion Malaysian ringgit and 37 million Malaysian ringgit per year respectively. The utilities part, which include the electricity, cooling water, processed water, and fuel. The electricity bill for this proposed plan design is estimated to be 2,478 and 77 cents. The cost for cooling water is 0.668 billion and for processed water is 69,175. Utilities cost for fuel is 0.354 billion. For the total cost for all having mentioned is added up to 28 billion Malaysian ringgit per year. Next, we will move to the cash flow analysis. The revenue is estimated to be 37 billion per year, where it has production rate of anhydrous acetic acid to be 1 million ton per year. Our company is able to generate profit for 20 years of operating based on our calculation. Based on the task given to us, we are successfully produce 1 million ton per year of anhydrous acetic acid and have a positive revenue. Next, we will move to the market analysis. The global glacial acetic acid is also known as anhydrous acetic acid is projected to register a CAGR of greater than 3% during the forecast period. Chemical industry, where the usage of glacial acetic acid is a solvent or an intermediate, was badly affected due to COVID-19 pandemic. Disruption in supply chains, declining demand due to the uncertainty in the global economy and capital market, and restriction of movement added unpredictable dimension to the chemical industry. All major top chemical manufacturers in the global market registered a declining revenue in 2020 last year compared to the previous years. Reduction in production of chemical thereby impacted the glacial acetic acid demand in short run. However, recovery state of production sectors of glacial acetic acid is predicted to positively impact through the years to come. And that's all for the costing part. We move to the next slide.
So as for the conclusion and recommendations, next slide, please. Thank you. Okay. In conclusion, our company aims to produce 1 million ton of anhydrous acetic acid using ethylene as our feedstock, using the method of direct oxidation. However, annually, Almager produces 88,311.6405 tons of acetic acid using 109,096.30 tons of ethylene, whereas it needs to actually produce 1 million ton per year using a feedstock of 698,598 tons per year of ethylene. Our product's purity is 99%. Our company operates 330 days a year, consuming 12,496.28 kg per hour of ethylene and producing 10,115.52685 kg per hour of acetic acid. By adding a recycle stream from the solvent recovery column in order to recycle MTBE and acetic acid, we were able to recycle 1,990.1349 kg per hour of MTBE and 140.21187 kg per hour of acetic acid, which helps with further production of acetic acid and reduces the time, cost, and energy used in our plant. As for the recommendations, first we could say that every plant design requires excellent safety measures. Units and equipment shall be checked and maintained regularly in order to prevent any leakage or consumption of components within the system which could really destroy the plant. Number 2, by finding a supplier that could provide most of our needs, transportation prices and tax costs could be reduced in order to help our companies increase our company's profit. And last but not least, a very important point to consider is the type of fuel which is used in the power plants. Currently, our company uses crude oil. Crude oil is a mixture of hydrocarbons that can be found underground in liquid phase. However, as we know, crude oil is harmful to the environment. By using biodiesel, which is a type of fuel that is derived from plants or animals, we can reduce the consumption of gasoline and diesel fuels that are made from crude oil. Biodiesel is known to be non-toxic and is also biodegradable, and compared to crude oil, it produces fewer air pollutants and is more environmentally friendly. Considering this, fuel costs, environmental harms, and pollution could be considerably decreased. Now we will proceed with our Aspen simulation video.
For Aspen simulation, the first thing is to input all the substance into the simulation. Make sure to choose all the formulas correctly. For example, the first input is ethylene. Click Next. And here we choose PSRK as base method. Next, we move to the simulation. The first unit is heater 1, where I input inlet and outlet stream. For this part, we will input values for stream 1 that include temperature, pressure, and mass flow rate for ethylene and ethyl acetate. Click Next to run the simulation, and then we will change the temperature change, which is set up to 125 Celsius. As you can see, there is no error and warning present. Back to our main flow sheet to add next unit, which is compressor. We will use isotropic compressor with efficiency of 0.8. Then the Aspen will run the simulation. Next is unit reactor, where we will be using our stored reactor. Now is the process of input the main reaction, where the fractional conversion of water is 0.05. Next, we move to separator unit. In this section, the mass flow rate of selective components are inserted at the outlet stream. Click Next to run the simulation. Then, for the light and column, we will be using DISTL unit in Aspen. Based on our calculation, we can put number of stages, feed stage, reflux ratio, distillate to feed mole ratio, together with condenser pressure and reboiler pressure. Then we can run the simulation. After that, the last column is solvent recovery column, where we put the STW unit. We can input number of stages, component for both light key and high key. Light key component is MTBE and heavy key is acetic acid. Following that, simulation calculation will proceed. We can see there is no warning or error present. For recycle, MTBE will be recycled from stream 23 to stream 19. which is inlet to heater. We will use S splitter to split stream 23 into recycle stream and purge stream. Recycle stream will be labeled as stream 25. Here we can see no error and warning during the end of the simulation. This is our full unit.
Thank you very much everyone for watching our presentation. We hope you have a great day.